Welcome to the Genius Factory. Enjoy the video.
You begin by confirming the prerequisites. Make sure the vector field is defined on a simply connected region and its partials are continuous. Next, compute the mixed partials, delta f1/delta y and delta f2/delta x, and check they match. If they do, the field is likely conservative. Once that test passes, choose a convenient base point, often set phi, x0, y0, equals 0 because you need an anchor for integration constants. From here, start integrating one component with respect to its variable. You now carry out the core calculation. Integrate f1, x, y with respect to x, treating y as constant, which yields phi, x, y plus an unknown function gy. Then differentiate this phi candidate with respect to y and compare the result to f2, x, y. This comparison isolates gy. Once you identify gy, integrate it to recover g, y up to a constant. Make sure to combine results and simplify. This gives a full candidate potential phi, x, y, ready for final verification. Finish by verifying your result. Compute the gradient phi and confirm it equals the original vector field f component-wise. If there is a mismatch, recheck algebraic steps, the domain's connectivity, and any dropped integration constants. Small sign errors are common. If uncertainty persists, pick two paths from the base point to a target point and evaluate the line integrals. If the field is conservative, they match. Once consistent, state phi up to an additive constant and document the base point used.
Thanks for watching. If you found this helpful, don't forget to like and subscribe.